Now, this is a very popular solutions-related stoichiometry problems that many AP chemistry teachers like to assign in their classes or use during their unit exams. So let's go right into this. Okay, so this shows that there is 0.150 grams a sample of solid lead to nitrate is added to 125 milliliters of 0.1 molar sodium iodide solution. Assuming that there is no change in volume of the solution, the chemical reaction does take place, is represented by the following equations. Now here, one thing to note is that they're adding a solid gram sample of sodium nitrate, which it itself is soluble. It confuses some students at times because it says S. This does not mean that it is insoluble. It actually just means that it's a solid powder that is yet have been added to a solution. In this case, the solution is sodium iodide solution, and there's plenty of water in there to dissolve that lead nitrate that shows as solid. So you can kind of think of this as this is actually aqueous, okay? So over here on the other side, you'll see that lead iodide solid is produced. That is the precipitate, and sodium nitrate is your aqueous so-called product. But we should know that these are just what we call spectator ions that come from the nitrates from here and then the sodium from here. So they should be floating around in the solution. So let's go right to question number 1. How would you know, it says here, list an appropriate observation that provides evidence of a chemical reaction between two compounds? There are generally a few signs of chemical reaction. Some of them are heat either producing or heat absorbing, light production, gas production, combustion. There's also, of course, precipitation. So in this case, the answer to this should be there should be new precipitate forming as a result. That should be the appropriate evidence observation that you see that shows that lead iodide is in fact being produced as a solid. Now B, it says calculate the number of moles of each reactant. This is a pretty straightforward process here. You do want to show the appropriate amount of work here. So you would start with showing 0.150 grams of lead nitrate, and to convert that into, say, moles of lead nitrate, you would simply need to divide that gram by the molar mass of lead nitrate. Now, if you look up on your periodic table, and you got to count the nitrogens and oxygens and all of that properly, you should add 1 lead with 2 nitrogens and 6 oxygens. Okay, so that would be approximately 331.2 grams. 331.2 grams is per 1 mole. I'm going to omit the unit just a little bit here. That gives us the mole. So 0.15, if you divide that by the molar mass given here, you should get a pretty small number, 0.0004529 moles. Now that should be rounded to 3 sig figs. So I'm going to go ahead and round that to 453 moles of lead nitrate. Okay. The other would be the matter of the other reactant, the sodium iodide. Let me go ahead and put this aside for the time being. And let's go to this. So you have 125 milliliters, and that is the molarity. So here's a little shortcut technique. You could take molarity times the volume. You always get moles. So that's the technique I'm going to use. Now I am going to take 125 milliliters of sodium iodide solution. Sodium iodide is NaI. Okay, and what I'm going to do is I'm going to show a little conversion from milliliters to liters. Okay, and then that's going to cross out the milliliters. Now let's go to the molarity. So molarity is 0.10 moles per liter. Now that is the definition of that molarity right there, moles over liters. So I can arrange it this way, which allows me to get rid of the liters. Okay, so that as a result, that should give me the number of moles of sodium iodide. So that should give me, I'm just eyeballing it here, 0.0125 moles of sodium iodide. Okay, that should be correct. Okay, so that's how many moles of sodium iodide there is. So let me just go ahead and put this down here. Not enough room to work with. So now it says here, C, identify the limiting reactant. Okay, one of these two is limiting. Maybe I'll just kind of make it smaller, put it up here. Okay, hopefully you guys can all see. Okay, which one of those two? Is it NaI or is it this moles of PbNO3? Which one is the limiting? I think it's kind of easy to eyeball this one because the mole ratio 1 to 2 tells you you're going to be using 1 mole of lead nitrate per every 2 moles of sodium iodide, and there's clearly far much greater moles of NaI than lead nitrate, even if you do have to use twice as many moles of NaI there is to lead nitrate. But you do need to show the work to support your identification. So I'm going to show that down here below. So I'm going to say 0.0125 moles, 0.0125 moles of sodium iodide was how many moles there were. And then I had 0.000453 moles of PbNO3 taken twice. Now there's several ways for you to figure out which one's limiting. One of the more readily used technique is have each one of these go all the way to the common product, which I will go ahead and set this as grams of PbI2, which is supposed to be my solid in this case. So why PbI2? Because I do make PbI2 solid in this particular case. As such, I guess it makes sense for us to go to the grams of PbI2. Now, I could go to the moles of PbI2. I just decided to select grams of PbI2 instead. Now let's look at the mole ratio in this reaction. Okay, between NaI to PbI2, so let me go ahead and use some colors here so you can see what I'm referring to there. So from NaI to PbI2, it appears that the mole ratio is for every 2 moles of NaI, I will be producing 1 mole of PbI2. Okay, now from here, if I wanted to find the grams of PbI2, I would need to find out the molar mass of PbI2. Now, lead is 207.2, I believe, and iodide is 127. That gives me a relatively hefty molar mass. 1 mole of PbI2 is 461.2 grams of PbI2. Okay, we'll do that calculation in just a minute. Let's do the lead nitrate one next. According to my balance equation, 1 mole of PbNO3 taken twice is to 1 mole of PbI2. And then I will do the molar mass yet again. Looks like 1 mole of this is 461.2 grams of PbI2. So if I were to go ahead and multiply these numbers together and divide appropriately, let's go to the 0.209 grams of PbI2 can be made for if I were to have started with PbNO3 taken twice. But if I had used the other reactant above, let me see what I get here. This comes up to be a much higher number, 2.88 grams, which means most of you guys probably already know the limiting reactant, which in this case this was 1, looks like this is the axis reactant. Limiting reactant is always the one that can produce the smaller, okay, of the common product when you're pitting one reactant against the other. So therefore, I think it's safe to say that lead nitrate is my limiting. Now, don't make any mistake here. It's not entirely the lead nitrate, but really what's limiting is the lead ion, which is the actual ion that is going to make the solid. Nitrate is actually just a spectator ion. Okay, now having said that, that leads us to number D. Like I said just a moment ago, nitrate is a spectator ion. So what is the molar concentration of nitrate? Going down here, knowing that there were this many moles of PbNO3 taken twice, you can argue that there is, okay, I'm going to just go ahead and take this, moles of PbNO3 taken twice, and for every 1 mole of that PbNO3 taken twice, there are 2 moles of nitrate ions found in there. And those moles of nitrates are not part of the net equation. So if you want to now turn that into molarity of nitrate, all you have to do is understand that the volume of this particular problem never changed. It was 125 milliliters. So I would simply need to take this moles at this time, because the moles of PbNO3 taken twice does cancel away. I just need to divide it by 0.125 liters. Just going to put a 1 up there. This should give me the concentration of the NO3 minus ion. So I would simply need to take that 0.000453 times the 2 and divide it by 0.125. That arrives at 0.00725 molarity. So it looks like that is molar concentration of my nitrate ion when it's all said and done. Okay. Lastly, on letter E, circle the diagram below that best represents the results after mixture reacts as completely as possible. Explain some reasoning. Okay, first of all, you got to eliminate the bad answers because the solid was PbI2. Once we get rid of that, we can see these are all pretty much appropriate choices so far. Here are 2 things that we can gather from this equation. We know their sodium and nitrate ions are spectator ions, as these are aqueous products, which means you need to be able to find sodium and nitrate in your answer choices. Now, based on that, it appears they all pass the bill because I see sodium and nitrate, okay, sodium and nitrate, okay, and sodium and nitrate. But here is where your understanding of access versus limiting comes into play. Earlier, we discussed that lead nitrate was access. Really, it was lead that was, lead nitrate was a limiting, and lead was the limiting, and iodide clearly is your access, which means whatever you choose, lead cannot be present in any of them, okay? Which none of them are. Oh, actually, hold on. There's lead. That shouldn't be in there, which eliminates this picture. Okay? Now we're down to picture 2 and 3. Now, the difference here is, the major difference is that there are iodides in this one doesn't have it. Now, because the access was the sodium iodide, iodide has to be an access ion. By that definition, it means there should be iodides left unreacted. As a result, that gets eliminated, and the third picture is the rightful choice. I hope this makes sense. Good luck.